Whether we like it or not, we are immersed essentially in a society, nationally and internationally, that's driven by technology, that's driven by devices and processes, communication linkages, transportation, household appliances, entertainment capability, and what have you, which is all dominated by technology. And design underlies all of that. If you don't design a product that's competitive, you'll lose that market.
Design is the ultimate bit of engineering. Everything else really serves design. But when you ask yourself, what is everybody doing what they are doing for in the modern world? I mean, we are not living in trees, plucking coconuts and bananas off the trees and eating them. We're doing all kinds of other things. And why are we doing those? Because of design. It's the only reason. It's technology is just a complete collection of the output of designers.
Design is the process of really solving a problem. It's not the process of writing about the solution to a problem. It's not just the process of dreaming about the solution to a problem. Design is the process that happens when someone tells you that you have to do it.
A design engineer takes enormous pleasure in producing designs which either on paper or preferably in hardware that work. You get an enormous thrill from putting something together that works well.
Design is improving the relationship between people and technology, considering all the criteria of aesthetics, of reliability and error, both human and machine, and of course cost.
One has to be engaged in the design process, in the innovation process, in the creation process over one's total lifespan. Children, infants, should be encouraged to design things.
Design is possibly the most important element in the achievement of progress.
Over the last decade, microprocessor technology has touched off a revolution in design practice. In the near future, design engineers will use powerful desktop computers with interactive graphics capabilities. Increasingly, engineers are using microprocessors as basic building blocks in products which are intelligent hybrids of mechanical and electrical components. Today, educators must meet the challenge of teaching students how to design this new generation of intelligent products, as well as how to take advantage of these powerful new design tools to stimulate creative thinking and insight. Design courses at MIT progress through 3 levels of sophistication. First, in an undergraduate course, students use a given kit of materials to solve a well-defined problem in a design contest. Here, the purpose is to design a device to put a cylinder in the hole before the opponent can. Second, in a senior level course, students must come up with a creative and economical solution to more realistic problems. This student team designed a sturdy, cost-effective oil exploration platform for the iceberg-plagued waters of the Beaufort Sea off Alaska.
What we're planning to do is just buy a carrier, some kind of big ship. It's roughly 200 meters by 30 meters wide. We're going to sail it up there. We're going to buy it used, which means that the price is quite low. We'll sail it up there and sink it in the ocean and use the decks as a platform.
You know, whatever it is you're doing as a designer, you can't, it's like if we just had equations pumped into us, for 4 years straight, and we went out and had a problem, we wouldn't know where to begin. But what we learn to do in design is how to approach it, and what kinds of things have to go into doing some sort of analysis so that you can do a design that will actually, work.
This way you go in off in a different direction. If you don't have to go all the way back and start something else. You can keep going, and if you get a different right answer, there are lots of right answers.
You get a chance to use your creativity. It's really not too creative, just solving problems from a book. But it's very interesting to try and figure out how to solve a problem by yourself. It's a lot more interesting too, really. It's fun.
It is fun.
Third, the graduate level course gives students experience in solving real problems submitted by industrial sponsors. They must define the problem, analyze it, propose a solution, build it, and make it work.
The problem was to design a system for an office tabletop copying machine that would take a stack of paper and feed it one sheet at a time to the rest of the machine. Now obviously there are a lot of systems like this existing, and the goal here was to make one that had a better price performance aspect than any in existence today. And specifically, the performance had to be fewer than 500 errors per million sheets fed, and the price had to be kept below $50 in a production form. And it's taught me a lot to think of creative things and how to really get things done, not just talk about getting done. Or it's one thing to draw out how something is going to work, but when he actually comes to making it, it's never going to work right the first time.
Throughout all levels of design education, interaction between student and teacher is crucial to the educational process.
Okay, what's going to happen when it doesn't work? How are you going to know it didn't work?
Right now, you haven't thought about that yet.
I mean, I suspect it could well work 9 times out of 10, but that 10th time you're going to have no bananas.
A mess, right? Because if it goes back and hangs this thing back up in the hanger without having cut the wire, you just you stretch the wire over there.
And then everything it does after that's going to take the wire with it.
Yeah.
Right. That's an issue, and I think unless you believe that it's going to work every time, you're going to have to give some thought to how you know.
Right.
In the computer-aided design laboratory, we're conducting research in 3 major areas. 1, the construction of 3-dimensional solid models through orthographic projections. 2, the modification of geometric models through variational geometry. And 3, the automatic scaling of assemblies of components. Geometric models are computer-based representations of geometry. They're used extensively in industry to perform drafting, analysis, programming of NC machine tools, and other related functions. Unfortunately, the most common medium for describing geometry historically has been 2-dimensional orthographic projections, such as shown here. This program that we're developing in this area's function is to take 2-dimensional orthographic projections and try to reconstruct the 3-dimensional solid which they depict. This program was developed to provide a more flexible and more natural means for modifying geometry, because geometry is changed very often in the course of production, from the time the designer first conceives of a part geometry to the time it's manufactured. It's altered many times, and we're attempting here to provide a very natural and flexible way of changing geometry. The third area of research involves the automatic scaling of assemblies of components. It is an attempt to develop procedures whereby the process of design can be stored in addition to the result of the design process. I'll show you what I mean. Every dimension, as shown here, has a rule, a decision rule that indicates how that dimension was chosen, so that, as is often the case, when the boss comes in later and says, I have to change the basic assumptions on which your original design was performed, such as changing the power of this transmission from 1 to 3 kilowatts, in future you'll be able to simply push a button and produce the new scaled geometry. These and other research activities pretty clearly indicate that the design profession is undergoing some pretty rapid and radical technological change right now. And we as an educational institution have an obligation to provide our students with an education that'll prepare them to both use this technology and to develop the design tools that neither you or I can even conceive of right now.
Golden Gate Bridge doesn't sway in a hurricane and destroy itself. It seems to work in all circumstances. It works very well. It also looks fantastically beautiful. And if I had designed the Golden Gate Bridge, I'd buy myself a little bit of land and put a cottage on it and just live there and look out the window.